Hello everyone. Today we're going to be going over this final question from paper 2 of the sample assessment material. I've been really excited to do this rates of change question, which is related to topic 9, calculus, and it is one single part which is worth 11 marks, and it's about finding the rate of change of volume from cone from the rate of change of surface area. So it's going to need you to use your intuition about calculus to quite a great extent to be able to figure out how to do this. Alright, so I'm also going to be talking about the surface area formula for a cone, because this is something that's quite unfamiliar to many people. And right, so let's get down to it. Figure 2 shows a right circular cone, so right meaning that the top is always perpendicular to the diameter, no matter what diameter you're looking at. And basically, the vertex of the cone is B, and the points A and C on the base of the cone are such that AC is the diameter of the base. The cone is increasing in size in such a way that the size of the angle ABC is constant at 60 degrees. So what this tells us already, that ABC is an equilateral triangle. So this side would be x, this would be 2x, this would be 2x as well. And the total surface area of the cone is increasing at a constant rate of 10 centimeters per second squared. So change in area over the change in time is always equal to 10. Find the exact rate of increase of the volume of the cone when x, the base of the radius of the base, is 6. So basically, first I want to go over what the formula for the surface area of a cone is. Obviously, the surface area of the cone is the area of the base, which is here pi x squared, and then the area of this actual conic part is a lot trickier to find. So imagine, I'm going to go up here for the explanation, but imagine you have the cone here, and you cut it up into tiny pieces like this. So you'd get a whole bunch of pieces which look like this. So stuff like that, but then this angle gets infinitely smaller. So like this length here would be L, and this length here would be whatever, some portion of the outside. And so if you, for example, if you cut it into 2 pieces, you'd get like this skewed thing and this skewed thing, and you'd add them together and nothing would really happen. So, but if you cut it into, say, 100 pieces, you'd get a continuing line like this, because we're going to arrange it in this pattern where the angle is here, then the angle is here, then the angle is here, then the angle is here, and the angle is here, and the angle is here, and so on, because that's how we would calculate the surface area of this conical part of the cone. And then finally we get to a point where the cone slices that we are taking become so extremely thin that this bottom and top of this parallelogram here become flat. And when this becomes flat, we know that the total radius must be all of these pieces plus all of this length here. So all of this length and all of this length constitute this line that goes around the whole base. So if this is the circumference of the circle, which is pi d, or 2 pi x, since our radius is x, and it's an equal, half the slices are facing upwards and half the slices are facing downwards, so their part of the circumference is down, so it must be split evenly between the top and bottom of this parallelogram. So one side is pi x and the other side is pi x as well. And then next you find that this length here, the parallelogram will start to approach the formation of a rectangle, so you can treat it like one since you're going to infinity. and this length here, length L, or 2x, since we know that it's an equilateral triangle, this is 2x here. And so the surface area of a cone, or since this is L, the surface area of the cone is the area of the base, pi x squared, and then plus the area of this parallelogram made up of slicing up all the outer bits of the party hat part of the cone. So in total, all of the parts of the circumference on here add up to pi x, as do all the parts of the circumference along here, and then the length of this is approximately equal to L, which is our slant height down the cone. And then we get that this part must be equal to pi xl, so pi x squared plus pi xl. Now let's go back to here and use this information to our advantage. The surface area of the cone is pi x squared plus pi xl. There are no marks for determining this during the exam. This is something that you're expected to know, but I'm going through this explanation because I can honestly tell you that I did not know this before looking at this question. Alright, so the area is pi x squared plus pi xl, and to justify that ABC is an equilateral triangle, we would have to have a justification that this angle and this angle are the same, which are too complicated to come up with right now. So what instead I'll do, it's not that complicated. It's just the fact that they're both connecting the base to the apex in a right cone. But what I'm going to do is use this right triangle they have given us with the knowledge that this must be 30 then, if this is 60. And so the length L, since sine is opposite over hypotenuse, and this angle is 30, sine 30 must be x over L, so L must be x over sine 30, and L would be 2x. So the area of the cone is that L must be x over sine 30, which is equal to 2x. Therefore, the area is pi x squared plus pi x times 2x, or pi x squared plus pi x squared times 2, or this is eventually equal to 3 pi x squared. Now, what you do next is we're going to try and find the change of x over time. So we know that dA by dt, or the rate of change of the surface area of the cone with respect to time, is equal to 10 all the time. But we also know, using some chain rule intuition, since for every little change in dx, dA must change by that same little bit, and for every little change in time, dx must also change to make that change in area happen. So dA by dt can be re-expressed as dA by dx times dx by dt. And we can find dA by dx algebraically. If a is 3 pi x squared, dA by dx must be equal to 6 pi x, just the power rule here. So 2 times 3 pi times x, because you're left with x to the power 1 after applying the power rule. So now we know dA by dt is 10, must be equal to dA by dx, which is 6 pi x, times dx by dt. And therefore, you can figure out that dx by dt must be equal to 10 over 6 pi x, or 5 over 3 pi x. Now, you may be asking yourself, where was I going with all this? Well, if we figure out the rate and change of the radius, we can use that to figure out the rate and change of the entire volume of the cone. So for example, if we look down here, we can find that the volume of the cone is 1/3 times the base area times the height, and we know that the base area is pi x squared, and we know that the height must be equal to, since it is the adjacent side to the angle 30, and we're looking at tangent, which is opposite over adjacent, so the opposite is x over h must be tangent 30, x must be, or rather, x over tangent 30 must be h. Therefore, since tangent 30 is 1/√3, x over 1/√3 equals h, and this means that h is √3x. So therefore, the volume V is 1/3 times pi times x squared times √3 times x, or this all boils down to √3/3 pi x cubed. And what can we do with this information? We're ultimately trying to find dv by dt. We know dx by dt, and now that we have an algebraic equation for v in terms of x, we can find dv by dx. So once we know that dx by dt is, if you are willing to look back up here, we'll find it's 5/3 pi x. Then you'll find that once we take the change in v for every little change in x, or dv by dx, this whole side here, √3/3 pi, is a constant, so we can kind of ignore it. And then x cubed differentiates to 3x squared, so this goes to √3 pi x squared. And then once we have this value of dv by dx, it will be √3 pi x squared times 5/3 pi x. So dv by dt, if we want to simplify this out, we can cancel out 1x here with the x down here. We can cancel out pi here with the pi down here. So we'll get down to √3x times 5/3. And if you go back to the very top of the original question, find the exact rate of increase of the volume of the cone when x is equal to 6. We just substitute x is 6 into this equation, so dv by dt x equals 6 is equivalent to √3 times 6, times 6, not x, times 5/3. The 6 and the 3 cancel out to give this a 2, and this √3 times 2 times 5 is 10√3. And we are done. So now I'm going to go to the mark scheme and check if we got this question correct. Remember, our intuition was to first find the rate of change in x, and then from there use the rate of change of volume with respect to x combined with our original value for the rate of change of x over time to find the rate of change of volume over time for x is equal to 6. And the exact rate of increase in volume is 10√3. Right, so let's go to the mark scheme and see if we were correct. So, yep, we determined that L is x over sine 30, which would make it 2x. A is pi RL plus pi r squared, so it's pi x times 2x plus pi x squared, which is 3 pi x squared. Yep, so we figured that out, and we got the volume of cone h is x over tan 30 is root 3 times x. Yep. So the volume is 1/3 pi r squared h, or 1/3 bh. Doesn't matter because this is an equivalent formula. So v is root 3 over 3 pi x cubed. Yep, we got that. And then dA by dt is 10 centimeters squared per second. This unit is in brackets because it might not be necessary. Then we find that dv by dx is root 3 pi x squared, and dA by dx is 6 pi x. This is quite an interesting way to go about things, because although it does check out, so you have dv by dx is dA by dt, and we want to get rid of dA on the top, and we want to get rid of dx on the bottom, so dx by dA. I suppose that is one way of doing it, but honestly I am much more partial to the way I did it, because that is how I logically figured it out the first time I did this question, because of course d something is representative of a very little change in something, and when you divide it by a very little change in another something, you get the rate of change of that something for every change in that something. And it makes sense to me that once we find every change in a for every little change in x, and we can then find this dx by dt, then we'll just use the chain rule to get dv by dx times dx by dt to get our final answer for dv by dt. I might do some videos on the intuition behind calculus after this, but then also my planned next series of videos, since this is the last sample assessment material question, I will be teaching that as well. So hopefully you guys can pick up some intuition for that, and then after that I'll be doing calculus, because apparently those are the two hardest topics, apart from maybe binomial expansion, which is not that hard after all. But then, yep, I'm going to be teaching trig, and then calculus, and this will also be aimed for those of you in core math who want to learn FP. Alright, so I digress. dv by dt is root 3 pi x squared times 10 times 1 over 6 pi x, so that's 5 root 3 over 3x. So that, substituting x in for 6, we get 10 root 3 centimeters per second, centimeters cubed per second. Lovely. Right, so our final answer here was correct. We got all these marks here. Remember, this is key, that the examiner will give you marks if your method is valid. It doesn't have to be exactly the one on the mark scheme, just has to be valid. Alright, so 10 root 3 centimeters cubed per second, and we have 11 marks. Alright, so I thank you very much for watching this series of sample assessment material questions, and I hope you will continue watching this channel in the future. Goodbye.